Let's get started. All right. So, if you can remember back, we had started talking about beam bending, right? And the first thing we really talked about with doing beam bending was how to figure out the shear and moment diagrams in the in a beam, right? Which we need to know to actually calculate the stresses. It's a little more involved to figure out the internal forces for bending than it is for torsion and axial. So we actually need to know the bending moment at a particular point. And so that's why we talked about that. But now, since we're able to figure out what's the internal bending moment and shear, but mostly we're talking about the internal bending moment at a point in the beam, now we need to be able to talk about how we can actually calculate the bending stresses, the stresses that arise from that. So that's what we're going to do today. Let me share my screen. Okay. So, okay, here we go. I think we started with the slide deck and we got through. We did all this stuff. So we talked about getting shear and bending moment diagrams, but now, okay, so now, well, maybe I should just back up. Right, so what we're able to do at this point is if we're given a beam with some type of loading, right, as shown here, we can then either by, analytical methods or graphical, we can figure out the shear force in the beam at every point. And here's showing the shear force. And then from that, we can also figure out the bending moment at every point, okay? So we need to know this because in this particular situation, you can see there is sort of a max bending moment that happens in the middle there, all right? Okay. So now we need to talk about, hold on one second, let me just fix this. I have no idea what's going on here. Oh, there it goes. Okay. Having issue. All right. So now let's talk a little bit about how we actually calculate the bending stresses, okay? So again, as with torsion, the first step is going to be making some assumptions about how the beam actually deforms, or in other words, the kinematics of beam bending, right? So here we have a beam before deformation, okay? And they've imposed a grid onto it. Also, you can see looking from the side, it's obviously a different beam, but they physically penciled in these planar sections, okay? And then actually we'll talk about this midpoint here, which is actually what we'll call the neutral axis. And then when we bend, obviously it deforms, and the critical assumptions that we make when we do beam bending, and this is why we call this Euler-Bernoulli beam bending theory, is we assume that these planar sections here remain planar. So you can see here when it's deformed, they're still in the plane. The planar section does not deform into something that's out of the plane like that, like a squiggle, right? So the planar sections remain planar. And then the second assumption is that they remain perpendicular to what we're going to call the neutral axis, or for now, we'll call it the midplane axis. So here's this midplane axis. And so these stay perpendicular to that midplane axis, okay? So those are our big assumptions. Planar cross sections remain planar. There's no warping out of the bending, and they stay perpendicular to that midplane, okay? The only type of straining we're going to see here, you can have the little highlight screen is overlapping it, but if you look at these sort of stretch segments, is that the planes or the lines going down the length of the beam are either elongating or compressing. So we're only seeing normal strain. And if you look at this, on the top, we have stretching. On the bottom, we have compression. All right. And that means that somewhere in the middle, we have no elongation, and that is called the neutral axis. Okay. All right. So those are our big assumptions we're making. There are cases where we have cross sections that don't stay perpendicular, and this is due to shear. And also there are bending situations where they don't stay planar, but it's usually pretty small, and these assumptions are very good, okay? So this is what constitutes our classic Euler-Bernoulli beam theory, okay? So now that we know how it deforms, or we've assumed how it deforms, we can start to talk about quantitatively what are the strains and then the stresses in here, okay? So here again is another view of an undeformed beam, and then it bends up, and you can see we have a little differential element here, dx. And this is looking at that dx from the side. So here it is looking from the side before deformation. So this distance here is dx, right? And again, we're going to see on the way this is bending here, the top region is going to compress and the bottom region is going to extend. And then there's a plane in the middle where it neither elongates or compresses, and we're going to call that the neutral axis, okay? So let's assume again that this line here is this longitudinal axis where there's no stretching. All right. And then you can see that if we take these two planar points and they stay planar, as in this figure, right? They obviously have to converge at some point. That is the center of curvature. And from that, we can also define a radius of curvature. So I'm going to call this distance here. This is the radius. So the smaller that radius is, the more bending you're going to see, right? Small radius, tight bending, larger radius, not as much bending, all right? All right, oh, here it is right here. The label that is wrong. Okay, now this is the plane where there is no stretching or compression. And so we're going to use that as our datum, all right? So up from that plane, we're going to measure the distance y to the fiber of interest, right? And so here, right, is the length of that fiber. Again, this is from the side after deformation, and here it is before deformation, okay? So in this particular case, if this distance here is dx, s has to equal dx, okay? All right. Now from this figure, I can also write that this distance here, which is the same unstretched length, that's going to be dx as well, because there's been no stretching on that plane. That is going to equal rho times the included angle, d theta, all right? Now, S prime, the length of this arc segment is going to be the radius to its point, this distance here, which is going to be rho minus y times the included angle. So S prime is rho minus y d theta. All right, so we know the length before deformation and the length after deformation. I should probably put a little differential in here, but so now we can actually use this to compute the normal strain. Remember, the normal strain is the change in length over the original length. So the strain that we would see at that fiber there would be the change in length, S prime minus S over the original length, which is S. So if we put that in here, I'm going to run it a little bit out of space. I'm going to write that up here, actually. Oh, this one doesn't have an eraser. So let's see if I can do this and fit it in here. So S prime is, well, you can see each one of these terms, S and S prime. If I put this into here, right? S is equal to rho d theta, right? So every term has a d theta, so they will cancel out. So upstairs, I'm going to have rho minus y minus rho over rho. And that's going to give me the following, that the strain is equal to minus y over the radius of curvature. All right. So if y is 0, we're right at this plane where there's no stretching. So the strain is 0, right? So, and as we go up in y, the way this is drawn here, we have compression. So as you increase y, the normal strain increases, but there's a negative sign there because it's in compression. If you go down in the negative y direction, you can see that the fibers are stretching. So you have a negative y gets multiplied by the negative in front of the equation. It becomes a positive. So you get stretch. So that makes sense. Also, if you look at rho, the radius of curvature, if we increase the radius of curvature, make it really large, the strain decreases. If we decrease the radius of curvature and make it very tight, the strain increases. All right. So all that stuff is kind of kept in this kinematic relationship. But, you know, I don't know what the radius of curvature is. Somehow I have to relate that radius of curvature to the actual moments applied onto the beam. So we're not quite there yet, but now we've used our kinematic assumption to get us sort of in the right direction. Okay. All right. So let's talk about how we can actually derive that flexure formula. Okay. Well, actually, before I get into it, so, you know, again, this plane where we're going to have no stretch, this is what we're going to call the neutral axis. All right. That's the plane with the strain equal to 0. There is no elongation or compression. Okay. It's where the strain changes from positive to negative, compressive to tension. Okay. And so we're going to use that as our data. So here we go. We're back to the same figure. All right. All right. So if we go back to this, do I want to do my neutral axis first? Maybe I should do the neutral. Let's do this slide first. Okay. So let's derive where the neutral axis is. Okay. Because I don't know exactly where that is. All right. All right. So if we were to look at this segment, right, we know that the strain is going to be something as follows, right? Minus y over the radius of curvature, okay? So it's linear, all right? And the stress is proportional to the strain through Young's modulus. And so that gives me a stress that's minus y over rho. So if we were to look over the cross section of a beam, if we were to cut it, okay, we would see the neutral axis where the stress and the strain vanish. And then as we go up in y, right, we get a compressive stress, and then that becomes an extensional stress. So if we were to plot the stresses across the cross section, we would see something like this. This is the stress due to bending as a function of y. And so we could write that again as the max stress times y over c. And the way I'm going to do this, I'm going to call this distance C, the distance from the neutral axis to the outer point where we have the maximum stress. So it's linear, so this is quite reasonable, right? So yeah, so if y equals C, we get the maximum stress. If y equals 0, we get 0, okay, for the stress. All right, but I still don't know where this neutral axis is. I don't know exactly where this is. So let's see if we can figure that out. All right, the thing that actually lets us find that is if we do a sum of forces. So on this section, the forces have to go to 0. It's in equilibrium. All right. And to get the forces due to that stress, if we look at this, right, each little, if we were to look at a differential force here, that is equal to the stress times the differential area. So the sum of the forces is actually going to equal the integral over that area of the stress times the differential area. We have this assumed stress field, so if we put that in here, this becomes area sigma max over C times Y dA. The maximum stress in C, those are constants, so this is equal to all right. And this has to go to 0. So obviously, I mean, if sigma max is 0, it goes to 0, but that's kind of trivial. If C goes, C has to go to infinity for this to go to 0, and so that's not going to happen, right? So what we need to have to go to 0 is this integral. This has to go to 0. Well, what does that mean? All right. So let's recall a second. If you recall the definition of the location of the centroid, so if we wanted to figure out the location of the centroid of some cross section, it is the integral of y dA over the total area. All right. So that's our definition of the centroid of some shape. So if you have a cross section, there's a centroid distance, right? And that's how you would calculate it. All right. Well, if we look closely, we can see this integral here that we want to go to 0 is right there. So if we're saying that goes to 0, then that is saying that YC is 0. Or in other words, the distance from the neutral axis to the centroid is 0. All right. Or in other words, more reasonably stated, the neutral axis is at the area centroid. All right. So the way we find out where the neutral axis is we figure out the centroid of the cross section. The neutral axis passes through that centroid, okay? And that's always going to be the case. If it doesn't, then, cross section is not in equilibrium, all right? So that's how we compute where the neutral axis is. All right, so now we know where the neutral axis is. Now we can actually compute what the stresses are, okay? So let's go back to this, right? So let's look at this cross section. So again, I'm looking over the end of the beam. All right, so we have well, I'll draw it this way. So we're going to assume that sigma y is equal to sigma max y over c. So this means we know where the neutral axis is. We calculate the centroid. This is the neutral axis location. And then the stress is going to vary linearly in such a way that it goes through 0 at the neutral axis. This distance here, we're going to call C. This is the maximum stress, and then it flips sign as we go through. So this here is sigma max. Okay. All right, so this is the traction due to our assumed stress field. That is going to be balanced by a bending moment. So the bending moment, you know, again, I'm assuming that this is going to 0. This is going to be a dx, right? It's a very small distance. So the bending moment, this is actually a negative phase. So a positive sense for the bending moment would be in the clockwise direction. So that's our bending moment. All right. And this has to also be in equilibrium. It's obviously in equilibrium if we do sum of forces. That's what we did to figure out where the neutral axis is. But we also have to have it such that the sum of moments equals 0. And then it'll be in equilibrium. So let's look at that. All right. So on the left-hand side, obviously we have the internal bending moment there, M, and that has to be balanced by the moments caused by the bending stress. So if you were to look at, oops, go away. If we were to look at some distance here, we'll call this Y. All right, there is a differential force due to that stress. That is sigma dA. That's the differential force. And it has a moment arm of Y. So due to this, right, there is a differential moment. All right, now that moment is going to go in the negative direction. It's going clockwise. So it's a negative sigma y dA. And now we can put into here our assumed stress. So that, you know, I get a y here and a y here. So this is going to become minus sigma max y squared over c dA. All right. That's our differential moment. So the total moment we get from the forces is to integrate that. So if we do our sum of moments for the whole section, we have the moment on the left-hand side. That's the, you know, negative moment, right? That's at the point X. All right. Then we have to integrate the moment due to the stresses. So it's going to be a negative because we get the negative here. Integral over the area, sigma max y squared over c dA. Okay. Again, sigma max and c are constant. Well, I'm sorry, this all has to go to 0. So I can get here m of x equals negative sigma max over c y squared dA. All right. Now we're going to do the same trick here that we did for torsion. We have this integral here. All right. And this is only involves the geometry of the beam cross section. So this is a lot like J. If you remember, J from torsion was the integral of the radius squared over the area. This is not the radius, but the distance y from the neutral axis squared. So this is, excuse me, this is called I, not J, but it's very similar to J. And this is the rectangular second area moment. Oops, area moment. All right, that's what we call it. Again, you know, most people just call it I, but technically it is the second area moment in rectangular coordinate system. Okay, so the rectangular second area moment, or sometimes people just call it the second area moment. All right. with respect to the y-axis. All right, so now if that's I can now get the maximum stress. Sigma max is now equal to negative m at x times c over I. And this is our first form of the flexure formula. So this tells us that if we know the bending moment in the cross section, m of x, and we can calculate from the geometry I and C, we can figure out that maximum stress that happens at the outer fiber. Now we can also take this and substitute it back into our stress equation, right? Sigma y is equal to sigma max y over c. And if we substitute this in for sigma max, you can see we get minus m of x c over I times y over c. The c's cancel out, and we get the stress as a function of distance from the neutral axis is equal to the bending moment at that point, the bending moment we would get from our moment diagram, y over I, with a negative sign out front. And the negative sign is there because, again, if we have a positive bending moment, right? If you think of a section with a positive bending moment, it's going to go like that and like that. That's positive bending moment. On the top fiber, we're going to get compression. On the bottom fiber, we're going to have elongation. All right. So the negative signs there, as we go up in y, it gives us a negative stress, a compressive stress. Okay. As we go down in y or have a negative y, we get elongation or a positive, a tensile stress. All right. So those are our two equations. All right. All right. So you're given a beam. All right. We haven't talked about it yet, but we will in a second, how we actually calculate I. We know the equation, right? We know that I is equal to, the integral of y squared dA. But we don't like to do integrals all the time, so we'll simplify that. We'll talk about that in a second. So you have the geometry of the beam. You can calculate I, and then you can also calculate either the distance to the outer fiber where we get the max stress, or you know at what plane you want to calculate the stress. From our moment diagram, you know what m of x is. So you can calculate the stress, either the max stress or the stress at some location, all right? That's the flexure formula. So now, knowing the moment, the internal moment in a beam, we can calculate the stresses, okay? All right, and we don't need to know the radius of curvature anymore. It kind of canceled out, all right? All right. So last little bit is how do we calculate I? So let's first do one for a very simple sort of rectangular cross section. This is going to be our, our simplified, this is the one we're going to use most often for bending, right? So I'm going to call this a beam. It's going to have this distance I'm going to call B. This distance here, I'm going to call H, the height of the beam. And so this distance here, C, is such that C equals H on 2. All right. This is obviously going to be our little differential area here, which is equal to B. How about I use B instead of D? B dy. So this is dy. Okay. All right. So I is equal to the integral over the cross-sectional area of y squared dA. All right. All right. So dA is b times dy. So now we got to integrate over the area of y squared times b times dy. And now, if you think about the limits of integration, it's going to go from y equals minus c to y equals positive c. We got to integrate over the entire cross-sectional area. All right. All right. So when we do this, we're going to get y cubed b over 3 d. Oh, I'm sorry. What am I talking about? D. Evaluated from minus c to c. Okay, there's the indefinite integral with the limits of integration. So it's going to be c cubed b over 3 minus c cubed b over 3. So minus c cubed is minus, is minus c quantity cubed is negative c cubed. So we get here is actually 2c cubed b over 3. And if we want to put in that c is equal to h over 2, then we're going to get that I equals 2/3 b times h on 2 cubed, which is going to give me b times h cubed over, well, I get an 8 downstairs, and the 8 cancels with the 2, gives me a 4 downstairs, so 3 times 4 is 12. So the I is 1/12 the base times the height cubed for a rectangle. All right. So again, we have units of length to the 4th power, inches to the 4th, meters to the 4th, millimeters to the 4th, just like with J, but it has a little bit of a different form. The other thing you want to see is if you want to make I large, you're much better off making h bigger than changing the width. Okay? So the area is obviously just going to be b times h. But if you want to increase I while holding the area constant, you should increase h. The value of I goes with h to the 3rd power. So it's much more influential on making I increased as opposed to b, right? So if you want to have something that resists bending, you're much better off having a section that looks like that than a section that looks like this. Trying to draw these with the same area. Okay, this one's going to have a much bigger I. All right. Okay. The other thing you can look at is actually, if you look at this value of the actual integral itself, y squared dA, again, because we have the y squared in the integral, having more material farther away from the neutral axis does us much better. So, that's why people like to use an I-beam for bending. All right, because here you can see we've added this material of these outer flanges as far away from the neutral axis as possible. So the area of material here does much more to increase I than the same area of material here in the middle. All right. So again, just like when we talked about maximizing J, you want to try to push the material out as far as you practically can. Now, obviously, there are other things like the space you have available to put the component in. Sometimes there's like buckling phenomena that might limit this, right? You can't have like an I-beam that's 6 feet high by 1/1000th of an inch thick. It's going to be like a piece of paper. Practically, those are limitations. But you always will do better by putting the material away from the neutral axis, okay? All right. All right. Any questions on that? So just in summary, right? I should have a spare slide I could just write on. We now know that the neutral axis is coincident with the centroid of the shape. Okay, so we know centroid. So that's where the neutral axis. And knowing the moment from the bending moment diagram and being able to calculate I and C, we can then get the stresses due to bending in the beam from the flexure formula. All right. All right. So we are almost there. There's just one last bit. And again, I always hate doing it this way because I have to do all these derivations before I can actually solve a problem. But, well, maybe I can solve a simple problem, but while I'm at it, let's just, you know what? No, you know what? Let me just keep going with this. All right. All right. So the last thing we need to cover before we can start to do the problems in the chapter is this concept of the parallel axis theorem. So very often we are going to have cross sections that maybe look like this, like a T or something. So I know how to compute I for a rectangle, but how do I compute I for something like this? Well, the way we can do this is we can break this up into two rectangles. This lower rectangle, rectangle 1, and this upper rectangle, rectangle 2. And we can get the I's for both of those. So I can calculate the I for this because it's a rectangle. And I can also calculate the I for this because it's a rectangle. The problem is the neutral axis in this case is not the same as like the neutral axis for just considering that top flange. Like if we were just to consider this upper flange, right? If we computed I equal to base height cubed over 12, well, let's say this is, we're going to call this H and this the base, right? That's fine, but that's computing the I about this neutral axis, okay? This one here. But I really need to compute it around the neutral axis for this shape. So how do we get the value of I when we shift the neutral axis? That's what we need to do. And the reason is so we can calculate I for these composite sections, all right? So, all right. So that's what parallel axis theorem does. So let's imagine here, I take this little top section and I'm going to draw it here as this little wedge, okay? So here is the neutral axis for that little section, and it's got a coordinate system X and Y associated with it. I can calculate I for that, right? But what if we want to calculate this around a different neutral axis? Well, actually, around this axis, this neutral axis. So I'm going to use Y bar to denote a coordinate system that's offset by the distance D from the centroid of that little shape, okay? So we can say that Y bar equals D plus Y. All right, so that's the relationship of these two coordinate systems. Okay, so if we want to get I for this little shape around this neutral axis shown here, it's going to be the integral over the area of Y bar squared dA, right? So I'm going to put a little bar over that to denote we want to get the value of I around the shifted coordinate system. All right. All right. So we know that we can substitute this into here. So if we do that, I'm going to get the integral over the area of d plus y quantity squared dA, which is equal to, oh, let's do it down here, right? The integral of d squared plus y squared plus the cross product term, 2dy, all integral over dA. And so if we break up each one of those integrals separately, with the first one, well, d squared is a constant, so that can come out. And we have just the integral over a of dA, so that's just the area. The second integral, the y squared has to stay in there. And I get y squared dA. So this goes to the actual area. Now this integral here, this is the value of I calculated about the y neutral axis, not y prime, right? So this is I, not I bar. So I'm going to call this I. That would be the I we would calculate, you know, if we were not shifting it. That's the unshifted I, 1/12 base times height. And then we have this last term here, which is 2 d integral of y a dA. All right. Well, if we look at this, okay, we know from, you know, when we derived the Fletcher formula, right? No, when we derived the sum of forces to figure out the neutral axis is coincident with the centroid, we said that this integral, the first area integral, has to go to 0, right? That's because the neutral axis is at the centroid. So that integral evaluates to 0. So now we got the integral, I'm sorry, the value of I about the new axis, the shifted axis, is equal to, all right, usually we write this term first. So we have the I about the unshifted axis plus this term here, which is d squared times the area. So this is parallel axis theorem. So if we want to get I around an axis parallel to the centroidal axis, shifted by this value d, we take the I calculated from here and we add on to it this term, d, the shift distance squared times the area. Okay, so we have an I and an area here. All right, and that's how we do it. So then we can compute the I for this section and this section about the actual neutral axis. We can add those together. Okay, so all right. So let's do.
Professor, I have a question.
Yep.
In this case, the area is of the entire, like, T. In this case, the entire T shape. The entire T shape.
No,
shape?
yeah, no. See, yeah. I'm using this as a motivation, right? So the area is going to be the area of this block here, okay? Because this is the area that we're shifting by parallel axis theorem. Does that make sense?
Okay. You're talking about,
because you could have multiple areas. There could be like, well, we might do some of these where there's like maybe 4 or 5 different little squares that go in to make the composite section, okay? And you can do the same thing if there's a hole. I'll do an example right now, but like if there's a hole, right? If this is a negative space, you could figure out the shifted I from parallel axis, but since it's a hole, it's going to be a negative. So you can subtract it off of the other I and get the, you know, you can get the I for these sort of composite shapes relatively easily, okay?
All right. Okay, Professor, thank you.
So let's do an example. Let's do, you know, the book kind of starts right off with doing some composite shapes. So I'm going to do like a really simple one just to start with, okay? Maybe. There we go. Where is my Zoom meeting? All right. So let's pick some values here, okay? So let's say we have the following section. So we're going to make a T section, all right? And I'm going to give this a dimension here of 1/2 of an inch. This dimension here is going to be 5/8 of an inch. All right. We're going to give this height of this section here. I know I can give the total height, but I'll just do this just to make my life a little bit easier. I'm going to call that 3 inches, and this distance here 2 inches. All right. Okay. All right. Now let's also assume at this point that, this comes from there's a beam here in some way that's, got some loading and whatnot, right? And what we know is that the bending moment at this point is going to be, let's say it's 100 pound-inches, okay? Find the maximum stress. Okay? This is a pretty typical problem. It's going to involve a couple of things, right? So obviously, we're going to use the flexure formula. But I need to get I and C, and we're going to have to use parallel axis theorem to calculate I and C. But also, even before that, we have to find out where is the neutral axis, because we have to do everything with regard to the neutral axis. So first step for these composite shapes is going to be define the neutral axis. Then I'm going to use that and calculate I, step 1. And then step 2 is to calculate I with the parallel axis theorem. So I'm going to break this up into 2 rectangles and add the I's up. Now I'll have I, C, and M, and the last step is going to be to calculate the maximum stress from our flexure formula, okay? So we have to do a couple little steps here. And also, if they had given you this problem with the actual beam loading, you would have had to even do a step prior to that. You would have had to calculate the bending moment diagram to figure out where the maximum moment is so that you can then, go through these steps, all right? So I guess in general, figure out where the maximum bending moment is, find the neutral axis, calculate I, and then calculate the stress, okay? So that's what we're going to need to do, all right? All right, so let's do it, okay? So I just want you to be clear about the steps we're doing, because I don't want you to get lost as I'm going through all this, detailed calculation. All right, so the first step, we're going to get the neutral axis. Find the location of the neutral axis. All right, so, okay. So again, we're going to break this up into 2 sections, okay? I'm going to call this section 1 and this section 2, all right? I'm going to call this base. I need to pick some reference datum. So I'm going to pick this bottom edge as a reference datum, all right? And I need to find where is the centroid of this composite shape. All right. And that's going to be where my neutral axis is, right? The neutral axis is the location of the centroid, but it has to be for the entire shape, this entire cross section, all right? That section plus this section, all right? All right, so we learned how to do this from statics. So the location of the centroid is going to be the sum of each little area times the distance to the centroid of that little area over the sum of the areas, right? So I is going to be either 1 or 2, right? It's the sum from 1 to 2. Okay. All right, so fine. Let's do the top, right? So for section 1, the area of section 1 is 1/2 of an inch times 3 inches, right? So the area for maybe I should just keep this here. Area for section 1 is going to be 1.5 inches squared, right? All right. Now, this is the distance from our datum, this bottom edge, to the centroid. Well, this is easy. It's a rectangular section. So its distance here, y1, is going to be 3/2. So it's 1.5 as well, but it's just inches. Does that make sense? I should have picked one that didn't come out to be the same number. That's kind of confusing, but right. This is here is the distance from our datum to the centroid of shape 1, okay? It's 1.5 inches. Now let's do the same for the upper T section, all right? All right, so the area of the upper section is 0.625 times 2. I can't do that in my head so easily. So that's 1/8. No, wait, that's not 1/8. What the heck? It's got to be 1.25. What did I do? Let's do this wrong. Oh, yeah, right. It's 1.25. Oops. And, well, I should just do this. So y for the first one is going to be 1.5 inches. And then the distance to the second centroid, right? From here, we go up 3 inches, and then we go up this half height here. So this distance here is going to be 3 inches plus 0.625 inches over 2, or in other words, that is going to be 3.31213, right? All right, so this is the second term here is going to be the area of the second section, 1.25 inches squared times the distance from the reference to its centroid, 3.13 inches. Yes. And that's going to be over the total area, which is A1 plus A2, 1.5 inches squared plus 1.25 inches squared. And so if we calculate that, what do I get? These are great things to do in a spreadsheet. And actually, I have a spreadsheet developed that I'll post on Blackboard to help with these things. But you really need to do a couple, manually by yourself, all right? All right, so here I get a value of 2.24 inches. So that means that, oops, well, I I hate when I do this. I always forget to clear this out. So the all right. The location of the neutral axis is .24 inches from the bottom. Now, you could have done this from the top. You could have picked the top as the local datum or anywhere you wanted to, but I usually just pick the bottom because it makes things easier. And so obviously the location of the neutral axis has to be 2.24 inches from that bottom, okay? All right, so now we know that. All right, step one, done. We know where the neutral axis is. And I've already got some of the calculations done already. Now we need to calculate I using the parallel axis theorem. So to get the I for the total shape, we need to get the I for the first shape, this one here. And this is going to be with parallel axis theorem plus the I of the second shape. So we need to get the I's shifted about the new neutral axis, all right? Okay. So actually, if you want, we should probably put the little over bars on these things, okay? All right. So let's first do the first shape, all right? We'll do this one first. Okay. So for I1, right, this is 1/2 inch. And this distance here is 3 inches. All right. So if we didn't want to shift it, the I of just that thing itself, the unshifted I, is 1/12 the base, 0.5 inches, times the height, 3 inches cubed, okay? So that gives me okay, this is 1.125 inches to the fourth, right? So that's the I for just that section. But now we need to shift that from the neutral axis, right? So here's the location of the centroid of that first shape, right? So we know it's going to be 1.5 inches from the bottom. So this here is the amount we have to shift. This is D for the first section, okay? And so that's going to be 2.24 minus 1.5. Okay, which is going to equal 5.74, right? So that's the shift distance, okay? So, depending upon how we draw the dimensions, you'll have to calculate a little bit differently, but you have to know that here is the centroid of shape 1. We need to figure out what that is shifted from the neutral axis for the composite shape. So that's why we needed the neutral axis. All right. So D for the first shape is 0.74 inches, okay? Now we don't really have to worry about whether it's plus or minus because we're going to square D, so it doesn't really matter anyway. So that means to get the I for that first shape around the neutral axis, it's going to be I of the unshifted shape plus D squared times the area, all right? Or now to put in numbers, 1.125 inches to the fourth plus 0.74 inches squared. And then the area, we calculated already, that's 1.5 inches, right? this stuff. All right. So what's the number we get off of that, right? So that means the shifted eye around the actual neutral axis is going to be 1.125. So this comes out to be 0.821 inches to the fourth. It doesn't shift all that much, okay? But that's because it's pretty close to the neutral axis. And then the total eye is going to be 1.946 inches to the fourth. All right, so that's the eye of shape 1 around the composite neutral axis, okay? All right, now we got to do the same for the second shape, for this one up here, shape 2. All right, so now we're going to do shape 2. Shape 2, this was an 5/8. And this distance here was 2 inches, okay? All right, so the unshifted eye for the second section is 1/12 the base times the height. So the base here is this dimension. That's the 2 inches. The height is the 0.625 inches. It's not very high. And we're going to times it by 12. So this eye is actually not going to be that big if you look at this, right? So I get for this 0.041 inches to the fourth. So that eye is much, much smaller than the eye for the leg, okay, the bottom part of the T. But let's see what happens when I actually shift it about the neutral axis. You're going to see that that's going to change quite significantly, okay? And it's going to be because the distance has moved, okay? So fine. So we need to figure out the shifted eye, right? So we need the offset distance for the second shape. So that's this distance here, right? This is D2. And so we're going to go up this distance here, which is 0.76 inches, right? This is 0.76 inches. And we have to add on to that half of this distance, which is the 0.313, right? So that is this distance here, right? Turns out to be 1.073 inches. And the area we already calculated as well. The area was, what was it again? 1.25, right? All right, so now we're going to get the shifted eye. This is the eye around the actual neutral axis. So that is the unshifted eye, this one, 0.041 inches to the fourth, plus the shift, right, which is D squared, 1.073 squared, times the area, 1.25 inches squared, and this has an inches in there. Let's see what that does. All right. All right, so this value here is 1.44 inches to the fourth. All right, so what do we know by that, right? So that shift about is much bigger than the eye originally, and it's like almost the eye of the other one. So then when we add these together, we get 1.48 inches to the fourth. All right, so here's the deal, right? So even though the I for that little T, top part of the T is not that big, 0.041, because we shifted it by over an inch, its value of I about the neutral axis has gone up considerably. And so again, that's the same thing I was saying. As you move material farther away from the neutral axis, it has a big effect on increasing I and then dropping the stress, okay? All right, so now I got the I about the two, let me just get rid of all this nonsense. So I got the I about for the two sections, right? All right, so now we can add those together and get the total I. So the total I about the neutral axis, right, is going to be the shifted value for the first section plus the shifted value for the second section. And so that's going to be 1.946 inches to the fourth plus 1.48 inches to the fourth. And that gives me 1, 2, 3.43 inches to the fourth. All right. So, okay, fine. So now we've got I, and we know the M, and we're in pretty good shape here. So now the only thing we got to do is calculate the stress. All right. All right. So we figured out where the neutral axis is from the composite section. We calculated the I's for each one of those sections, and then we shifted them to get the I about the actual neutral axis, then added them together, got the total I right here. That's the I we're going to use in the flexion formula. So now we're almost ready to calculate the stresses. So we're going to do the third and final step. Okay, but let's just take a little bit of a break, and I want to talk about something here, right? So let's go back and look at this cross section again, right? And I kind of deliberately glossed over this earlier, all right? Okay, so here's our shape. It has a total height here, right, of 3.625 inches. And we know the neutral axis is here at 2.24, was that what it was? 2.24 inches. All right, so it's a positive bending moment, right? We put on this section here, it's a positive bending moment, so it looks like this, right? And here's like our top part of the T, right? So this is our M equal to 100 pound inches. So up here, we're going to have compression. The stress is less than 0. And down here on the bottom fibers, it's going to stretch. So we're going to have elongation. The stress is going to be greater than 0, all right? And then we got a neutral axis. All right, now before I always said that C is the distance from the neutral axis to the outer fiber. But in this particular case, we have two different C's. We've got, here's the neutral axis location. So it's 2.24 inches down to this bottom fiber where we get elongation. And then going up here, it's going to be the 3.625 minus 2.24. So this is 1.385 inches. So here's my question. Where will we see the maximum stress? On the top or the bottom? Anyone want to take a guess? I should do a poll. I never know how to do polls in Zoom, but is anybody there?
Should it be the top as well? Why wouldn't it be?
Well, this is farther away, the bottom, right? So if we were to look at the cross section, right? I'm gonna exaggerate the difference, right? So here is like looking down the side, right? And so here's the T, right? There's the little edge of the T. And I'm going to deliberately draw I'm going to like exaggerate the neutral axis. The neutral axis doesn't go right through the middle, right? It's closer to the top. Yeah. And we know the stress is 0 at the neutral axis, right? And it's going to go on a straight line path, right? So where's there, who has the greater absolute value, on the top or the bottom? It's going to be on the bottom, right? Because this distance is greater. This is the 2.24 inches. And this is the 1.38 inches, right?
Okay.
So you can calculate the stress at both of these points, okay? Up here, it's going to be a compressive, and down here, it's going to be tensile. But it's going to be greatest here because that is the point that is the furthest away from the neutral axis. So when the section is like symmetrical, like maybe it's an I-beam, right? In that case, the neutral axis goes right through the middle, and those values of C are the same, right? So even though a 1 will be positive and 1 will be negative, they will have the same value on the top and the bottom. In this particular case, down here, we're going to get the max stress. Now, it's going to turn out to be a positive stress, but I'm not saying max stress because it's positive. Maximum value, absolute value, okay? All right? So it's always going to be the point that's farthest away from the neutral axis. So, fine. So we can calculate that. So this is where we're going to get the maximum stress. So the maximum stress, so like if you want to, we can call this C2, and this is C1, right? Top and bottom. And C2 is greater than C1, so we use that. All right, so the maximum stress is going to be the bending moment. Now this is going to be MC on I, right? So M is 100 pound-inches. C, we're going to use this value here for C because we're going to figure it out at the bottom. We're going to figure out the bending stress at that bottom edge. 2.24 inches. And now we use the I for the composite for the entire cross section, which we got from the parallel axis theorem. This 3.43 inches to the fourth. All right. Now, in the numerator, we're going to have pounds times inches squared. In the denominator, we're going to have inches to the fourth. So that's going to give us pounds per inch squared, or a PSI, right? And what do we get here? So here it's pretty low, but I get 65.3 PSI. And it's going to be a positive because down there it's elongating. If you wanted to figure it out at the top, we can get the stress at the top. The bending stress at the top. It's the same bending moment, 100 pound inches, but we're going to use the distance to the top. That's this, the 1.385 inches. And it's going to be compressive, so there's a negative sign out front, and it's the same I. And that gives us a value of here I get negative 40.4 PSI. All right. So it's a little bit less. It's in compression at the top. Okay. If the moment had been flipped, right? If the moment was going the other direction, say it's a negative bending moment, then we would have had compression on the bottom here and elongation on the top, but still the max stress would be on the bottom because that still is the furthest point from the neutral axis, right? It's still 2.24 inches away from the neutral axis. So you would have gotten the same values, but just the signs would flip, okay? Any questions on that? So kind of a couple of steps. If you do get one, actually, I looked for, I consider probably the preliminary problems. Like if you have a cross section that's like that, well, it's pretty easy to do. You can just, you don't have to figure out the neutral axis. It's right in the middle, and you can calculate I as just 1/12 base times height, right? But most of the time, you're not going to have such a simple cross section. You're going to have one of these sort of composite cross sections. So you'll have to do a little bit of work to calculate where the neutral axis is, and then to calculate the actual I, which will just be the I for each of those little sub shapes, and just shifting my parallel axis there. Okay. All right. Let's do, there are a couple of things that can make your life a little bit easier if you look at them, because I don't have a ton of time, but let me just mention this. Imagine you have an I-beam like this. It doesn't look very good, but whatever. So it's supposed to be symmetric, right? So let's just say this is 2 inches, and I'm going to say this is 3.5 inches. And each one of these things is 0.5 inches, right? All right. Now we want to figure out I for this shape. Well, yeah, you could break this up into 3 sections and figure out the I for each one of those. And it's actually not that bad. If you look at this, right, the neutral axis, it's symmetric. So the neutral axis is going to pass right through the middle. That one's easy to appreciate without actually doing the calculation. So this is going to be 1.5 plus 1. This is 1.75, right? And this is also 1.75. And you can just shift the top one. But the other way to think of this is you can think of a box like this and then subtract out the little side cuts. I know I'm not doing this very well. Do you see how, if we subtract out these negative I's, right? You're left with the I-beam. So neither of these have to be shifted. So this is, we can just get the I of this is 2 inches by 3.5 inches. So the I for this one is going to be 2 inches times 3.5 inches cubed over 12. And then we're going to subtract out the I's from these. So if you think about the I's from this one, this height here is going to be 2.5 inches. And this distance for each one of these, well, actually for the total, add these two together, it's going to be 2 minus, let's say this is also a half. So that's going to be 1.5 inches. So this would be 1.5 times 2.5 cubed over 12. So you actually don't have to do parallel axis theorem. You can just subtract the negative. And since all those shapes have their centroids coincident with the neutral axis for the I-beam, you don't have to use parallel axis theorem. The D's are 0. It's a little easier to calculate, okay? So don't forget sometimes using that trick for the negative areas. Also, I didn't derive it, but a couple of times you'll have a circular cross section. So here we have some diameter D. So the I here is going to be pi over 64 diameter to the 4th. All right. It's going to be half of J. All right. Pretty easy to show why that is, but for us, that's what it's going to be. Okay. The neutral axis obviously goes right through the middle, and that's how you calculate the I, pi over 64 diameter to the 4th. Okay. All right. Well, I'm sorry I didn't do too many problems today, but we got through the majority of the stuff that's actually in this chapter. All right. So I will do, there's a homework assigned. All right. And then on Tuesday's class, I'm going to do nothing but problems from this chapter. Okay. Because I covered all the material, even though I'm not a big fan of doing all the lecturing, but now we're through it. So try to do some of these problems, you should be good. If you have questions, you can post them on Blackboard. And then Tuesday we'll do problems. You probably can imagine I'll have you in groups, and you can probably imagine I'm going to have you guys submit the problems at the end of class. Okay. All right. Any questions? All right. Well, have a good weekend.
You too.